Okay, started. Yeah. Okay. So we started discussing about the limitations of AlexNet that we will see today in detail. One is the vanishing gradient, another is the possibility of overfitting. Now, what we mean by overfitting, maybe that also we mentioned that when your model is outperforming, it is very good in terms of training data, but the test error is high. So in that case, we term that as overfitting, and we mentioned that the possibility the why there is a possibility of overfitting in your model. It may happen some noises, some disturbance in the training data itself that is also getting captured, and your model is getting trained based on that also, incorporating that disturbance, these fluctuations also. And whereas in these data, that fluctuations may not be present, and that's why overfitting is coming into picture. Maybe till that part, so far I remember that part we have discussed. Now, someone asked that day that what may be the possible solutions of this overfitting. We'll start our discussion today from that part. That one possible solution can be that data augmentation. Okay, that means very easy. Fake data is generated and added to the training set. It is mainly basically the concept is you are basically adding some add not exact noise but some some added features that may be not exact feature of your training data, and that you are adding to the data augmentation. Okay. Next one is parameter norm penalties. You are adding some penalties associated with a loss function and to optimally limit the capacity of the model. Next one is dropout. Some connections, they are randomly dropped out and they are randomly put to zero at every iteration. Okay. The final one is the heavily used, that is the cross validation. We term it sometimes as k-fold cross validation. K signifies the number of groups. That means in your training data itself, you are splitting them in few groups, maybe in k groups. That from that the term comes, that is the k-fold cross validation. And in those part of them, you are treating as your training data, and the rest you are treating as test data. And that way, you are basically resampling and you are modifying your training data set, and you are that way you are testing whether your model is working fine or not, and you are making it free from this type of overfitting. So these are a few options when you are trying to handle these overfitting issues in your model. Okay. Now next come the most heavily used problem when we talk about this type of DNN models, feed-forward models. That is the vanishing gradient problem. Now, what does it mean, and why do we need this vanishing gradient problem? First of all, I think this is, from our initial discussion, it is clear that in general machine learning, what we are doing in the classing approach, we are basically treating this type of features separately, like edges, like this gradients, etc. Separate features we are considering. Based on that, we are training our network, and on top of that, on the test data, based on those features, we are trying to predict. Whereas in case of neural network, there is a concept of forward neural network or feed forward path. What does it mean? Whatever we are discussing, that the components we have discussed, basically they are the part of this feed forward path. If we take now the convolution, if we take now the pooling, if we take now the all this normalization, these components together, they are forming your feed forward path. Okay. Now you just take this here a simple example where, let's say, from your based on your kernels, your filter choices, you have initially chosen some weights, and based on those weights, that weights you have actually applied on your input matrix. Inputs, maybe in straight way you can think in this way. You are applying those weights on your inputs. On top of that, you are applying some bias, and then you are passing that output to some activation function. And this way, it is forming your feed forward path. Okay. Now this part this is a general equation, how you are representing the output of one path. You are basically multiplying with this with input, bias, and then passing this with the activation function. Okay. Now what happens in the training scenario, what you are doing basically, you are choosing this type of weights, choosing some kernels, and then you are basically applying these operators, basic operators what you have on following these steps, and you are getting some output. Here you can see there are some outputs given. Now in your training phase, what is the difference between training and testing phase? In the training phase, you know what may be the output, what should be the actual output. And then in your training phase, applying some weight, you are basically checking what output you are getting. One is predicted output, one is actual output. Okay. And you are checking what is the difference between this predicted output and maybe we have. Okay. Predicted, you can see better here also. You are checking here the difference between the predicted output and the same diagram. You can see now the same summation of your weighted inputs and then passing to the activation function, and you are getting some output. Now what happens whenever you are getting this predicted output, you are checking the difference between the predicted output and the weighted output. If there is a match, gradually you are accepting that weight and you are storing that weight. That is the output basically coming from your training phase. These weights you are applying in your testing phase, and then you are getting some output. That is your test output. In the test output, you can understand your inputs are unknown, right? Their levels are unknown. So there is no possibility that you can actually verify whether you are getting the correct output or not. But in training phase, you are constantly doing this type of checking whether your predicted output is matching with your actual output. If it is getting matched, your weight, whatever you are chosen, that is acceptable. Otherwise, you are considering that difference as an error, and you have to update these weights. So anywhere in here also, you have to update these weights. Okay. So this is the basic idea of, we term it as back propagation. Okay, this is the basic idea of back propagation, where what is the objective? Basically, anyway, the objective of our training phase is to get the correct weight that we can use in the testing phase, and we can predict the value correctly. So that is done by this back propagation phase and weight updating. Okay, is there any question so far? By the way, I forgot to ask. Is there any question? All right. Now you check this one. This one we are doing on a simplified. Basically, we are doing on a network where we are not only considering output coming from the previous layer, we are also considering some temporal inputs. This is a bit advanced version of whatever examples we have taken, whatever models, networks we have considered before. But if you also remove this part, this concept of temporal inputs, then also whatever we are going to discuss now about this vanishing barrier problem will hold good. Okay. So we are thinking this type of network where we are getting some outputs from the previous layer, and also we are getting some inputs, some temporal inputs. At some timestamp t1, you are getting this input. At timestamp t2, you are getting this input, and so on. So with this, whenever we are getting some output from previous layer, we are multiplying that with some width, and then we are getting some output to the next layer, O1, O2, O3. And they are also getting passed through some activation function. So you can see here the general representation of this output. That is, your input, this temporal input, is multiplied by some weight, whereas your previous layer output is also multiplied by some weight, W1 and W. For sake of generalization, we have just considered W and we have just considered W1 here. Okay. For all the weights, we have considered W1, but that is not always true. This may vary, and this Wi, I mean, you may think at that time maybe Wi and Wj. Okay. Fine. So that means for each output, we can represent now as x11 for the first level output into W plus O0 into W1. And you are passing that through your activation function. You've chosen, we have mapped that as F. See here, the F is the activation function. And this activation function, I hope now it is clear, it may vary based on your application. You may choose a sigmoid, you may choose a tanh, you may choose softmax, whatever, maybe based on your requirement, this F will change. Now, in your training phase, you are interested to compute whether you are getting the actual, whether your predicted output is matching with your actual output or not. If let's say it is not matching, or if there is a difference, we are actually computing this loss. That is y hat. Y hat is the predicted output minus the actual output. Okay. So with this, since this predicted output, this loss is dependent on this predicted output, what we can get directly, we can get this derivative of loss with respect to our predicted output. Okay. But what is, I mean, why we are doing this, why we are doing so much calculation? We are interested to get that how I will update the weight. What will be the change in the weight? Maybe there is some, constant factor, maybe learning rate. I have not written this, but I'm interested to get some amount of, to check what will be my change in my loss for a particular value of weight. So here you can see at the output at the last phase, we have considered the weight as W double dashed, and based on that, what will be my loss? It should get multiplied by some learning rate, and that part I will subtract with my existing weight, and that way it will update my weight in the next iteration. So this is the basic idea how from my back propagation or in my training stage, I am basically based on our difference between predicted and original output, I'm updating the weight. And finally, when we will complete all the iterations, we will get the output, modified weights, which we will use in our testing phase. Now, when we are computing this loss, derivative of loss with respect to this with respect to W double dash, that is the weight at the last stage. By chain rule, this can be expanded by this rule, that is chain rule. Sorry, chain rule. We can actually expand this with this form, this derivative of loss with respect to y hat into these terms. This derivative of y hat with respect to this with W double dashed. Okay. Similarly, if you come now to this part, whatever inputs you are considering, the temporal inputs, x11, x12, x13, all this for all these inputs, you are associating some weight W. Okay. Now this loss with the change of, when you are interested to check the loss with respect to this W, similar expansion you can form where you are considering the loss derivative of loss with respect to y hat multiplied by derivative of y hat with respect to your output 4, because that is your final layer output. And then you are multiplying that derivative of output 4 with respect to the weight you are considering at this stage. That means you are considering the derivative with respect to the weight, the final stage weight you are considering. Now you think this will go on. For this layer, only these 3 multiplications are sufficient. Okay. When you come to this layer, you will expand, you will again incorporate some more multiplications in this chain rule followed by this chain rule. And there you will consider the derivative of this O2, then derivative of O1, derivative of O0, and so on. So that means these multiplication terms here, they are gradually increasing to compute this whole derivative value of your loss. Okay. Now these terms, if you see, they are very small. There are 2 things to observe. These terms are very small. Whenever you are computing these derivatives, you are multiplying very small numbers with again one even smaller numbers. This is one thing. Another thing is that if you now observe these terms, this O4 is, as we have just shown here, O1, O2, etc. This O4, again, it is following this similar representation. It is dependent on the activation function, F, whatever you are choosing. So based on that, when you are performing the derivative, what type of activation function you are choosing, that also affect your this multiplication result. And again, it will also dependent by how many layers you are considering. See, whenever you are increasing the layers, the number of the inputs, the multiplication, number of multiplications are basically increasing. So that way, effectively, these values, maybe I should. That way, these values will be gradually decreasing. And once it is decreasing too much, it is at some point, it is so negligible that this is not contributing much in this update equation of your weight parameter. And if you are, and at this point, the meaning is that your gradient is decreasing in such a way. That's why we are terming it as vanishing gradient. It is decreasing in such a way that at a certain point, it is vanishing. And that way, your weight parameter is not updating properly. Sorry, not properly, I should say. It is not updating significantly. That means at some point, you need to have some significant amount of these gradient values so that it should contribute in a significant way to update your weight parameter. Then only you can, from previous step to the next step, then only you will get some change. Because if your weight parameters are same, every time if you are using the same weight parameter, it is expected that for same inputs, you will get same y hat. Your loss function will be same. That means the training steps are not going well. You are not getting exact parameters, exact weight parameters that you can basically transfer to your test module. I mean, test step to do high accuracy prediction. So this is the problem for deep learning network. Whenever you are increasing these layers, whenever you are, it is a concept that if you increase the layers, of course, theoretically your accuracy should increase. But in a practical scenario, this updation of weight parameter, that is getting hindered, and that is not contributing significantly to your test parameter generation. And that way, this problem of DNN that is shown in AlexNet or any, whenever you are increasing layers, you have to keep in mind, you have to check for this, whether it is actually contributing to any kind of this kind of vanishing gradient problem. If your gradients are vanishing, that means for your training is not going well, you are not getting proper parameters to fit in your test network, and then your testing will not be accurate as you are expecting. So this is the general problem you will see in many cases of machine learning. In this type of AlexNet, this type of VGG, in many this type of with huge layer solutions in DNN. There is a problem of vanishing gradient. This problem, that is a limitation they consider. Okay, is there any question? Is it clear, or should I repeat it once again? Can you hear me?
Yes, ma'am.
Yes, ma'am.
Okay, it's clear, right? So
Yes.
okay, so you can see here now whatever we are discussing last day. Yeah, so that's why it was mentioned in case of AlexNet features that ReLU was employed as a non-saturating activation function to improve the convergence rate by alleviating the problem of vanishing gradient. Actually, AlexNet, this is the important feature why we should tell before AlexNet that ReLU, usage of ReLU activation, it was not very common. It was that time sigmoid is there, and for sigmoid, that's why I was telling that whatever activation function you were choosing, you can see here whatever activation function you are choosing, that will highly impact these these components, and that in turn highly impact whether you are facing this type of any vanishing gradient problem or not. So that way ReLU is a better choice compared to sigmoid, and this ReLU was first introduced as AlexNet feature, and prior to that people were mainly used to sigmoid or these type of activation functions. Okay, so now we have some understanding, I think, about overfitting, what we can do overfitting for a solution. Someone is asking cross validation, that is a good solution, a more generally used solution in case of overfitting. And vanishing gradient, we will talk much about this, some other type of networks where we can see how this can be solved. Okay, and then other features are use of large size filters compared to previously proposed works. And due to efficient learning approach of AlexNet, it is significantly important. It got significant importance, and it has, it was treated as the backbone, the first layer of next coming literature of CNN. Okay. So next, that we have already mentioned, that use of some large size filters. So compared to previously proposed works, and now come to the, we will discuss when we are talking about, maybe this is not exactly related to AlexNet. We will see this changes of filter size in VGG when we will discuss about GoogleNet. But first we should have some idea that what we'll have, why we are thinking about filter size, why we should not fix one filter size, and we can use that always. So in convolution, what happens? You under now I think you know that this way you have your input matrix, you have some filters, and 1, 2, 3 equals. So what we do, we have these filters, we do some multiplication, and then we slide, and so on. So a convolution filter slides over all the pixels of the image, taking their dot product. Okay. Most of the useful features in an image are usually local, and it makes sense to take few local pixels at a time to apply convolutions. So that means whenever we are thinking about some local features, it should happen that the full local feature you should capture. The first requirement is the filter should not be very small. We will see about 1 cross 1, but they are not very much significant to capturing. They are just passing on information, but not capturing very much the some feature, because for some localized feature to capture them, you need to have, should have the filter size of some significant amount. Okay, and these filters, again, as we mentioned, the same features you may found in different places of your input space. That means you have to slide and you have to perform the same operations, the multiplication, with the same filter, only the input matrix, inputs coming from the your pixel matrix, that will change. Okay. So single kernel all over the image are used to extract the same feature in different parts of the image. Okay. So whenever we are using that very huge kernel, that means for each and every slide, we are supporting huge amount of computation, because the more you increase this filter size, if you are making it 4 cross 4, 5 cross 5, of course you have to support that type of, that number of multiplications. You know, when you are multiplying with 3 cross 3 and when you are multiplying with 4 cross 4 filters, your multiplication numbers, that is increasing. So that means if you are using, the basic idea is that if you are using small filters, you are saving in terms of computations. Okay. Benefit from weight sharing and reduction in computational cost. But your filter should not be so small that it is not fully capturing that localized particular feature. So that way we have to use, it is important to use this, this choice of filter just size is very important to extract some amount of features. Also, another thing is that you will always see the general, these filters, they are not so much bigger size, and on top of that, their width and height. That means you will see 3 cross 3, 5 cross 5. This is the reason to support this type of odd numbers, because we are trying to encode the pixels in the neighborhood of source pixels. So you have maybe for the feature, You don't know exactly what are the number of, pixels that are supporting the exact feature. But you are not only focusing on the exact feature pixels, but also on the neighborhood. And with that, source pixel is the anchor point at which the kernel is centered. Okay. And when you are centering something, your odd, some filters with your odd width and odd height. That means odd size kernels. They are proper, they can be properly centrally placed. They can be considered to be symmetrically shaped. Otherwise, what will happen? Let's say this is, if you are considering, let's say 2x2 filter. In that case, the center you cannot identify properly. Whereas when you are considering this 3x3, you can actually focus, you can actually consider the symmetry of the shape, and you can actually consider the centralized behavior. The kernel is centered and we are encoding all the neighboring pixels accordingly. So that way, it is better to choose this odd number size and width as a filter and to apply that. So you will see in general, whenever you see this filter size, you will see 3x3, 5x5, and so on. But this discussion, we will see more when we come to this, observations of VGG, next GoogleNet, etc. But in AlexNet, what they have done, they have compared to LeNet, they have increased both. They have increased the layers and they have directly increased the size of the pixels. Size of the filters. You can see the size of the filters are very large, 11x11, 5x5, but still this odd property was maintained. Now, one thing is that so far whatever we are discussing up to LeNet, AlexNet, here whatever so far done, it was done based on some heat and trial. That we are doing something, we are increasing some parameters, we are increasing some features, and we are getting some high accuracy. There was not much analysis that what is going on, what will happen if in case of AlexNet, I do not use this going from 11x11. We just change it to 7x7 or 5x5. So what will be the change? So that analysis, or why it is happening, the change, why it is happening, what is the mathematical or the supporting background of that. So that was not much analyzed. Whereas starting from 2013, okay, just stop me, okay, if you have any question. In JFNet, starting from 2013, that analysis came into picture, and that was the onset of DeConvNet. Okay, in DeConvNet, it works same manner as whatever we uses the order of convolution and pooling operation. Okay, and there was some reverse mapping to check the visually perceptible image patterns. That means there is some analysis what is going on. On top of AlexNet, basically you can think DeConvNet, this is the extension of AlexNet, nothing else. But here it is there is some reverse mapping applied to check whenever we are applying some strategy, applying some filter size, what is the visually perceptible image patterns. So that is the idea in ZFNet, you can think. And in ZFNet, from this analysis, few observations were made. Few observations were actually it was found that it showed that whenever we are considering these layers, only a few neurons were active. In contrast, other neurons were dead in the first and second layers of the network. That means whenever it is obvious, right? Whenever you are considering the first and second layers, some neurons actually becoming active, and the last coming, whenever we are proceeding, the other neurons, other related features, they are getting active. So this was first formally observed in ZFNet. Also, another observation was made that reduction of filter size and reduction of stride to retain the maximum number of features. That also can be meaningful. That means, so far in LeNet, we consider some layer, some filter size. In AlexNet, the improvement is that, okay, increase the layer and increase the filter size. In GFNet, we are first observing what will happen if we are reducing some filter size and reducing the stride, and what will be the effect on that accuracy. Hello? Hello? Can you hear me?
Yes, ma'am, you're audible.
Okay, so sorry, my net got disconnected. Wait. So can you just tell me how far this slide have you, I have explained, have you heard it? This ZFNet?
Ma'am, slide is
Yes,
not visible.
but the
Not
slides are
visible.
not visible now.
Okay, wait. What happened? Can you see my screen? The shading, can you see?
Yes, ma'am.
Okay. Can you see the slide now?
Ma'am,
Yes or no? Can you see the slides?
No, ma'am.
no, ma'am.
No. Okay. Let me log out and log in again. Can you say it now?
Yes, ma'am.
Yes, ma'am.
So, have you heard? I have discussed about ZFNet. So, have you heard up to that?
Ma'am, we had till the part that we reduce the filter size and size of stride. Up till
Okay. Okay. So that was okay, fine. Okay. So what are the so that was the observation coming from ZFNet that if we reduce the filter size and if we reduce this number of the stride, then what will be the effect on accuracy? Now, nowadays, if you see, we do not use ZFNet much, but the observations made by ZFNet this model was very significant because that affected the next upcoming the CNN modules, that is VGG or GoogleNet. I think these names are very heavily used or heavily known to us. So in case of VGG, we will see what type of changes were considered. Okay. So this VGG and the GoogleNet, they are the outcome of some this type of CNN related challenge. This is the and CNN that time VGG stood second, and then the GoogleNet came up as first. So then VGG, which was proposed in 2015, it was made use that it was a modular in layer pattern and 19 layers deep compared to AlexNet. So 5 to 8, then we came to plus 19. Okay. And what is the main meaningful observation that was used here? That is, as ZFNet suggested, the small filters can improve the performance. Based on these findings, VGG replaced these large filters that was present in AlexNet with some stack of smaller filters. Okay, and experimentally demonstrated the improvement with that use of this 3x3 filters. Okay, the another improvement is that in AlexNet we have seen that AlexNet that is used over LayNet, it used the activation function, the ReLU activation function. Here we are getting the softmax. The softmax, this mathematical function, it is mainly that is a you can think that is a improvement of argmax, where we are basically considering it is suitable for multi-class classification tasks. Where you can think that as it is a mathematical function that converts a vector of numbers into a vector of probabilities. That means now this VGG, you can understand that is suitable when we are thinking of multi-class problems. And when we are trying to do this multi-class classification, we are getting a vector of probabilities, and these probabilities will signify that for multiple class representation, which will be the chosen one, which will be the second chosen one, and so on. So that way, the softmax was introduced in VGG, and it is giving the expansion of using the CNN in multi-class classification problem. Okay. So some other changes are there. The max pooling is placed after convolution layer. You know that why pooling is important. And another addition was a padding was performed to maintain the spatial resolution. I think now you all know what are the meaning by these components, but how, I mean, what is the importance and what was it first used and when it is important, that part we are using. Now padding means this type of, this padding layer is added. Now, why this padding is important? You can see this input coming from input matrix, and this is your filter. Now, whenever you are applying this filter on this matrix, you are getting this output. And if you check this too, the dimension of this input and dimension of this output, you can see there is a significant reduction, right? This is 4 cross 4 and it is coming to 3 cross 3. That means whenever you are doing this type of filter based multiplication, you are basically getting some a dimensional reduction. Now, whenever you are designing a network, if this dimension reduction is not, it is not in all the parts of the layer, throughout the layers, and it is sometimes it is difficult to design the network with such sudden dimension reduction. And that's why the padding is important. When you can see when you are actually adding this padding, this padding is added here, and you are basically considering this part, and then you are applying this you are completing this multiplication, filter based multiplications. You are getting this output. It is retaining the previous dimension values, the height width, that it is retaining the previous dimension values. That way, to maintain the dimension. And also another research, another paper that time, it showed us that another significance of this padding, that to keeping information off at the borders. Otherwise, if you do not use this, it was shown that if you are not using this padding layer, we can say, the border information, this border pixel values, they will actually vanish just after one operation. They will vanish. So whenever we are basically sliding the filters and we are repetitively trying to fetch the effect of that filter, we are repetitively trying to fetch the features and the whole input space, that will not come, because this border information, it will vanish too quickly. So to keep this border information and to keep its effect while applying repetitively the same filters, this padding is important. And another importance of padding is that we can maintain the same dimension, the dimensions of the input throughout the network with the usage of this padding. Okay. So these are the main significant, changes that was made in VGG. One is the reduction of filter size. Another is the usage of softmax, so that you can use that for multi-class problems. Second one is padding. You can retain the border information in a better way. You can handle the designer network better with some, fixed dimension. So these are the improvements made on VGG. Okay. Similarly, okay, before that, we should mention about the VGG limitation. Okay, but it required a huge parameter. Okay, so which made the VGG computationally expensive, because you are using actually smaller filters, but you can see here you are using stack of smaller filters, and with that number of parameters increased, but it showed good results. It showed some amount of improvement in terms of classification localization problems. Okay. One similar direction of research, actually it came in the same in parallel, actually GoogleNet and the VGG, that came in parallel, where GoogleNet proposed one inception block. Okay, this is the structure of inception block. The main idea is that nothing but that all this GoogleNet, and why we mentioned ZFNet first, because this GoogleNet, VGG, they all got inspired by this ZFNet, outcomes, observations, and they started looking how they can use this smaller blocks efficiently, smaller filters efficiently. So here also you can see that in BGG we have seen stack of 3x3 filters. Here there's a concept of split, transform, and merge. So whatever inputs you are getting, there are some they are going they are actually getting splitted, and then you are performing this 1x1 and 3x3, this type of convolutions, and then finally the results are getting concatenated. You can see here 3x3, 5x5 in different paths. This type of this different types of filters that was added, that was multiplied with the previous layer output. Now there is one observation about this new one. 3x3 we can understand. Okay, there will be some feature extraction. Yes. Then
In this diagram,
yes.
the different branches of this diagram may learn different high level or low level features.
Yes.
Then how is this concatenation being done?
Okay. I'm coming to it. Before that, I will say one thing. Okay. First is that before that, one answer is that why this 1x1 convolution is being used. I mean, what is the 1x1? If you see, that is basically just can take the same pixel and that can pass to the next level. But in 1x1, it is basically appending, or it is fusing multiple. Okay, before that, maybe we have already mentioned about multiple channel concepts, right? In colored images, especially, we talked about RGB, multiple channels. So through this 1x1 convolution, they have basically fused this multiple channel inputs, and on top of that, these convolutions are applied. Okay. So you can now, if you see there, if you are applying 1x1 convolution, you are fusing all the channels, some for particular features, and then you are applying some 3x3 convolution. Okay. Next one, again you are doing that same, and then you are applying another type of 5x5. Actually, you are applying separate type of filter, and again you are doing some different convolution. Okay. Then you are doing some max pooling. We all know that why pooling is important, and then we are doing the convolution. Here you are just fusing the effects of what to say, that from the multiple channels, and then that data is getting passed to this concatenation layer. Okay. So basically, when we are doing this 3x3 or 5x5, these are basically coming from related kernels. Maybe you can map them with some particular features, but these feature maps we are generating fusing all these channels. It is not separate, because previously it was done separately. For the art channel, we are applying some filter, we are getting some output, etc., etc. But here the change is that we are fusing the effects of 3 channels, and then we are, you can think this way, we are separately extracting features. So that for that, this 1x1 convolution is important, and then we are passing that to this concatenation layer. Okay, that means we are initially, this is just one basic architecture of inception block. But if you go and check the actual architecture of GoogleNet, this is not the whole architecture. This is just a one simple block where you are splitting, then you are transforming, and then you are merging with the original formation too. So whenever you are doing this concatenation, now you have some information about the feature for which you have applied this 3x3 convolution. Now you have some detailed information about this 5x5 filter. Then you have done some max pooling, because pooling is for some rotation, etc., some other features, and then whatever feature, direct features are coming from this RGB total channel. After that, this concatenation is done. Okay, is it, is it something related to your answer?
Ma'am, partially, ma'am. I was actually thinking that suppose this 1 by 1 convolution is there,
Yes.
then this 3 by 3 convolution, this is one branch.
Hmm.
Then there is this 1 by 1 convolution and another 5 by 5 convolution, that's another branch. So
Yes.
these branches might lead to formation of or extraction of different kinds of features.
Features, correct. Yes.
Now, in concatenation, like how do we exactly concatenate these
Okay.
features together?
Okay. First thing is that whenever you are going to this concatenation layer, this is not your last layer. Okay. So maybe in this basic first block or first level, you can think about this one basic architecture in that in a particular level. Maybe next day what we can see once the whole GoogleNet architecture. Then this part will be clear. So here we are in this concatenation. We are basically taking some initial features, and we are based on that we are getting the feature maps. Along with that, we are also taking through this 1x1 convolution the whole inputs coming, some fused inputs coming from the three channels, so that on top of that, on that information, we will again do some other convolution in the next layer. Okay, maybe this is one part of your answer. Maybe next day what we can do, I will get this whole architecture of this GoogleNet. Then you will better understand why this we are talking about this split and merge. Basically, the basic concept is here that we are splitting and the merging. That is the idea. Okay, and how exactly we can go to the concatenation layer, maybe next day we will go on this.
Okay, thank you.
Okay, okay. So far, I think whatever we have talked about, you have seen CleanNet, AlexNet, this GoogleNet, ZFNet. So we are doing this. We are thinking about that spatial that we talked about in the last day, that spatial exploitation. We are changing in terms of the filter size. We are changing in terms of arranging the filters, and then we are doing the spatial exploitation. Next comes the depth-based CNN. Here we will again go back to that same problem, our gradient descent problem. There we mentioned the problem, okay, but now we have not talked about any solution to that specifically. We have seen that for a particular number of layers, this GoogleNet, this all these structures, they are working fine, okay. But what will happen? Basically, here we will discuss one highway network after this, where we will see that there will be specific strategies that will be incorporated so that we can at least handle 50 layers with a better convergence. Whereas in GoogleNet, we are actually working with this some 22 layers. So there is a difference. So whenever we are moving to this much of depth, we will be now talking about this depth-based CNN. That means we are increasing the depth now. We are increasing the number of layers. But we know that if we actually, blindly increase the number of layers, then we will face that type of vanishing gradient problem. So what is the solution? Well, how we can handle that? That is the main answer we are going to give in this depth-based CNN. Okay. So for that, one approach is highway network. Okay. So highway network, it is an approach as it is written, what I have already told, to optimize the network for increasing depth. Okay. So it is also multipath based CNN. We will talk later exactly focusing on this word, why we are talking this as multipath. You can leave it now. But you can see here that this is the increase 50 layers from 22 layers to jump to a 50 layers. Now this highway networks, basically they work based on some gating mechanism. Okay. In that gating mechanism means that in a simple way, it is a since from name suggests a highway. You have one main road. Sometimes you are bypassing the main road, you are taking the highway. Now that when your highway will be open, when your main road will be open, that can be handled by some gating mechanism. Now to understand this gating mechanism better, we first discuss about this LSTM a bit, then we will come to this, what exact gating mechanism we use in highway network. Okay. So it is used in text sequence leveling, speech recognition. We will take one example, then maybe we'll understand it. Okay, so let's first talk about this long short-term memory and what type of gating concept we are getting from this LSTM. So when we talk about this, first we think maybe this one we talked in our first slide. Remember first day when we talked about some kind of feedback in CNN. That time I mentioned that just keep it now. We will discuss it later. So this is that part where we are considering some neural network which is having loops. Okay. So you can see this is your network and you are having some input, temporal input at a particular time. You are considering that input xt, getting output, but this loop is getting associated. So here is one example why this is necessary. So it is written that humans don't start their thinking from scratch. So there is some relation every time. Whatever I am telling to you, whatever networks like Google Net, VGG, whatever I am explaining to you, I have to make you explain before what was there. Why AlexNet is coming from LiNet? Why Google Net or VGG is different? How the concept is coming? If I do not skip the ZFNet part, of course there will be a gap. So humans don't start their thinking from scratch. They develop step by step. But in traditional neural network, they cannot classify what kind of event is happening at every point and how it is affecting the next part. So whatever previous discussions, previous examples we have taken, we are just classifying one particular image, whether it is a car, whether it is a house, etc., etc. But if we are taking applications like this speech recognition, language modeling, or what if you are trying to predict what ma'am is going to tell in the next line, maybe you are predicting now, okay, the next slides will be something related to this related recurrent network, how we are going to implement, how we are realizing this. So from your previous experience, from this slide, you are basically predicting your next upcoming slides. So in these type of predictions, this recurrent neural network RNN will be meaningful. Okay. So what will happen? Of course, if you are unrolling this neural network, you can see at a certain time, these are related to some temporal inputs. Your model is working based on some temporal inputs, and it is giving output, giving some temporal output, and it is also giving some input to the model when it is working on the next temporal input. This one. So it is basically sending that you can think as a feedback, that you can think as a loop. This model is not only whatever temporal output is input is coming from outside. The model itself is actually, the network itself is giving some input to describe, to properly understand the next temporal sequence. So this way you can think about unrolling how you can think that how one recurrent neural network may work. That means if though I have not described anything, you can understand in this network you have some input coming from the present time and you have some input coming from, that is the output based on the previous temporal input. Okay. So that we will see. Okay, here one example is given. You can see, I grew up in France. I speak fluent French. Okay. So recent information suggests that the next word, so I grew up in France, this word may predict this word French. Okay. So that is the recent information suggests the next word is probably the name of a language. So that's what I have given the example of the next coming slides. Whatever we are discussing, that from that you may predict the next coming slides. So with this understanding, what we need when we are talking about this type of temporal dependent network, or we are talking about long short-term memory networks. Here, this is a special type of RNN, recurrent neural network, that is handling this or learning and handling this long-term dependency. How it is handling? See, it is considering some temporal input xt. Here, it is taking output from some previous temporal inputs, and based on that, it is basically affecting the network, and it is controlling the network, how it will work, how it will react, how it will predict when the next temporal input will come. Okay. So we will see here, this is a clumsy network. You can see, we will see step by step, one by one. What does it mean? So that to better understand why we are telling it as a related to something memory, long short-term memory. What does it mean? Okay. So this is we term it as a sales state of LSTM. Okay. So LSTM, what it can do in this cell state, it can carefully regulate the cell state, and it can remove or add information to the cell state. Okay. Now, when we are talking about removing or adding information, of course, we have to do anything here. We have to do it by activation function, and that's why this activation function, this sigmoid activation function, that is very effective, because what we know, the sigmoid gives output 0 or 1. If you pass some value with this sigmoid, it will either pass some 1 value or some 0 value. So when we are talking about this sigmoid outputs some numbers between 0 and 1, so this will signify, this output will signify that how much from the each component, how much will go through. So output is like, this is like this type of 0, 1. Sorry. So when we were actually applying this type of activation function, so you are basically denoting how much of the information can actually pass through. Whether the information will fully pass through. If it is 1, it may fully pass through. If it is 0, set this output is set as 0, then nothing will pass through. There is a total cut. Like if your main path is cut off, there is a cut off in your main path, you are taking the highway. Now, maybe when we will be discussing our highway network, you can think in this way. So when we are introducing this concept of cutting something, or we are introducing the concept of allowing something, we are basically using carefully this sigmoid activation function. A value of 0 means let nothing get through, while the value of 1 means let everything get through, and in between it will regulate the output. So if that is clear, now the next steps are, there is nothing, you will understand it. So when you are trying to predict the next word based on all previous ones, you have to decide which all the inputs you will consider and how far that will affect your next level input. So you can see here, okay, if I go back here, this clumsy part, you can see here, in all these parts, this sigmoid is present. Okay. Now this sigmoid, the why this is important, you can see the first part in your cell state. it is taking xt, that is your temporal output at that point. This is ht minus 1. Okay, this is coming, the effect coming from your previous temporal sequence or previous temporal input, and all these two are getting your weight factor, then the bias. Okay, that means in a it is looking into this ht1 and x2 and outputs a number between 0 and 1. Okay, so the idea is, whenever you are actually applying this xt, okay, this ht minus 1, this input coming from your previous output, it is controlling how far of your this element, I mean how far information of your present element will actually pass through. Okay, similarly, if you come to this part, this it, okay, it is also same thing. Okay, but here one tan h is associated with it. That means tan h means it is some expanded version. It is restricting its level between 0 and 1. Tan h is not so much restricted. So the next step is to decide what new information we are going to store in the cell state. Okay. So first one, language model trying to predict the next word and which part we will allow coming from the previous part. So it is coming from the previous part. The second part, this component is basically controlling which part we are allowing to affect our previous part. Okay, how many, I mean, it is regulating. This is just directly coming to output. Okay, you can see here, then you can understand maybe this part. So this first part, actually this slide is important. 1 second. Just see this carefully. The first part, this part, it is controlling how much of your previous input you are basically passing to the next layer or next temporal observation or next temporal sequence. This part basically considering how far your previous input or previous previous output, previous layer output will affect your present input. Okay, so that's why it is, you are doing some sigmoid operation and then you are doing some tan h operation. Okay, and this part is how far of your present input you will pass to your output. So these are three basic operations forming this present layer of your LSTM. So first part, how far, you can see here also from this equation, from your previous output, how far you will let go to affect your final output. This is how far, how much of your previous output will actually affect your present input. And this part, the final this third part, it is basically how much of your present input you will allow to pass your third input. So there are three steps. Previous output is affecting your present input. Previous, some part of your previous output is going directly to the output, and some part or fully, maybe full or maybe according to your regulation based on this sigmoid function, some part you will allow of your present input xt, you will pass directly, you will feed pass directly, and that will define your final output. So with this tree, you are basically forming this output CP. Here it is not shown. I will add one more slide when we'll update. So whenever you are basically computing this output CT, these three components are actually summing up, and together they are forming the final output. Okay, so that way, in this case, I mean in LSTM, basically it is acting as a memory. Why we are telling it is as a memory? Because when you are the controlled by the control you are putting with the sigmoid function, you are allowing to forget some components, some part of your previous coming from your previous output. You are allowing to forget some part of your present input, and you are allowing to forget how much you are allowing to remember or forget, whatever way you may think, how far your previous output will actually affect the present input. Okay, so these three components finally forming the output of your this cell state. So that's why if you see here this CT, here it is basically dependent on this function, this FT into this CT minus 1, that is your previous output, and plus additionally this part IT into this part, it is coming from your present input. So that way you are actually handling, you are taking this gets, you are basically, you can tell in this way, you are using this activation functions as your regulators to allow or to disallow information to your next step. Is it clear? Is this part clear? Or do you have any question?
Ma'am?
Yes.
Hello. Ma'am, what are these temporal inputs in terms of a real scenario?
Temporal means timing based, like maybe you are dividing your inputs at 1 second, you are considering 1 second, 2 second, 3 second, and you are getting xt minus 1 here, xt here, xt plus 1 here. So maybe in a time series you are considering the inputs, and that inputs you are feeding to this LSTM network. Okay.
Okay.
And how your previous input or previous output of your network is affecting your next output, or next output. So that is that control you have, and you can make based on this activation functions. So this is the basic idea of LSTM networks. That's why we term it as memory. So this memory is sometimes allowing you to remember something, storing something, or passing. Remembering means what? You are passing that information. If the sigmoid output is 1, you are passing some information to the next layer as it is. That means you are storing that in your memory. But when this is 0, you are basically stopping that information to pass. That means you are erasing the information from your memory, and that way you are basically that's why it is this is called that at that time this is a forget cell. Okay, so this is the basic idea of LSTM network. Now you see, since you have now this gate concept, do you have any more question? First of all, let me ask. Okay. So once you have this concept of remember and forget, the same thing we use in our highway network. Okay. So in highway network, we have this concept of gate. Okay. Maybe this you can see here the model has 2 gates in addition to this is your highway gate. This is your actual transfer function. Okay. Any desired transfer function we are planning, that is H, this H that is taking the parameters width and your X. Now in highway network, you have added 2 gates. One is the carry gate and one is the T gate. Okay, C gate and T gate. Now when Now, of course, you can see the relation, the C get is equal to 1 minus T get. That means once this T get is on, or T get is 1, the value it holds, if it holds the value 1, then 1 minus 1, then means that time the C get, that carry get, will be 0. That means this T get means this transform get. So whenever you are transforming something, the carry get will be 0. It's like this is like a highway. Whenever you are, this is maybe your T get, if this is on, this path is on. If this is 0, then only this path is on. Then you are passing that to the sorry, this is C, carry get. That means if this path is off, if T is equal to 0, that means carry get is 1, and then this path is on, and you are applying that highway network. So this is the basic structure. Just see this whenever you are the structure of the hidden layer, how you are getting the output. This is your transfer function. This transfer function, let's say if T is equal to 1, that means this part is only active. That means H into T, only this part is passing your H, the actual transfer function. And if T is 1, of course C, this part will be 0. Okay. Then there will be no, output coming from this carry get. So similarly, if C is on, you can also check the vice versa. That means when C is on the other hand, that means you are passing this X input directly to this output. Then that time this Hx, the effect of this transfer function, is basically 0. Maybe it's clear, right? See, if this part, this CXWC, if this is 1, that means obviously this T part, it is 0. That means this H into T, this part, this will be 0. That means this X, it is directly getting transferred to your output value Y. That means this X will be the direct output of your hidden layer. Otherwise, this X will be passed through this transfer function. That means X is getting modified with this weight factor, and that output will be transferred as that output will be transferred as the output of your hidden layer. So that means in highway network, the concept is you have two gates. If one is open, you are directly passing the input to output. If that is closed, that means the carry gate is closed. That means your transfer function gate is open, or transfer gate is open, and you are passing this X input through some transfer function getting applied, and that will be the output of your hidden layer. It is basically one layer of control what you are getting. You can think in this way also. In a simple way, if you are thinking about this transfer function as a sigmoid function, that means once your carry gate is open, your C is on, that means you are just passing the full, whatever input was there, you are passing that to output. Your Y will be your X. But whenever that carry gate is closed and you are passing that your X through some transfer function, now that transfer function will control how much or what type of output you will actually pass to Y. So this is the concept of highway network. Now we will see how it is meaningful to actually reduce the gradient descent problem. Just directly you can think that if some case by layers, our gradient, vanishing gradient, the problem was that whenever there are huge number of layers, this del value, this delta value, it is decreasing, and we are getting some very small value here. Okay, very small value to update the width. But if now you are passing this, you are actually opening this carry get, and you are directly passing this x, this input from here directly, then the value, it will be not so small, because that is not a derivative value. This is not a very small value. It is directly passing that comparatively large value you are actually passing to this layer, and that is basically contributing to update your width. Okay, this is the basic concept we use when we talk about these depth-based networks. That is same in ResNet. Now, if you see what we understand by residual learning, maybe you heard about ResNet. Okay, ResNet is based on exactly this concept of residual learning. Okay, and this ResNet, I will come back to the importance of this ResNet, but just to explain, the same highway network concept, the extension of that is, incorporated in this ResNet, and there we are terming it as some residual learning. Residual learning means, see here, your input is getting passed through some weight layer, then you are passing it through some values, some activation function, okay, and then some weight layer, and then you are coming to some next layer. Along with that, you are basically passing this x. This we call as identity shortcut. This is nothing but this x value you are directly passing here. So along with this weight, along with this activation function, and then applying derivative to it, whenever there will be some degradation, when you are directly passing this identity shortcut, basically you are boosting up this value here. And that is used to handle, because in gradient descent problem, you had the problem that your values are gradually vanishing. It is becoming so small that it is not affecting much to update your width. But here, when you are passing this value directly, you are bypassing this x value here. Basically, you are boosting up with this identity shortcut connection. You are basically boosting up that value, and that will help to handle this vanishing gradient problem. Hence, we are telling that gradients can flow through the shortcut connections to any other earlier layer. And that is the advantage of, highway network. That is the advantage of ResNet, and this is the basic structure of ResNet. So whenever we will be talking about later on, maybe we will be directly referring to some residual learning, we will directly referring to some highway network. We should understand that means we have some bypass path, we have some bypass connection, and the main purpose of that just to handle this gradient. Okay, is it clear? No response. Very difficult, to understand. Is it okay? Do you have any question?
Ma'am, is this connection same as a skip connection?
You are basically, okay, there are two things. When you are talking about skip connection, you observe here, you are basically doing this. You are not skipping anything. You are basically adding this identity shortcut with your existing value. Okay. So in some cases, you are actually just skipping this value and you are just passing this shortcuts. That time you can think of some kind of skip connection. Okay.
Concatenating, right? We are adding the values.
Exactly. We are adding the values. We are concatenating. We are not skipping in it.
I had one to here. Ma'am, when the input X will go through the weight layers, its dimension change, right?
Yes.
So we are adding two different dimension vectors.
But there will be some steps to handling the dimensions. That is later on.
Okay.
Okay. But here we are just talking about, we are passing that information. That information got degraded, but we are passing that information there. After that, we will handle that dimension and we will feed that to the next layer.
Okay, ma'am.
Okay. Okay. Anything else? So these are two main things we wanted to discuss today. So this is the why vanishing gradient problem and what is the solution. Maybe this how highway network or this type of this identity connections can solve this problem. Along with this, there are a few combinations because you know, right? Last day we were also telling that every day we are having some new machine learning or deep learning algorithm. The basic idea is that here you are there is this inception ResNet, inception VP. There are a few other names where there are little tweaks with this what we say with this filter size, with this combination of this inception. In inception ResNet is very interesting where we are having some merging of these two concepts, inception block and this residual connection, that is this passing of that direct connection. So these concatenation. While coming to DenseNet, you can see another improvement. This is pretty simple. If you have understood DenseNet and you have understood that why this type of highway path or highway network is important, then in DenseNet, what it is telling, in ResNet, we are telling, okay, we have combined the identity function. We are basically concatenating, as you have mentioned, identity function and the output. Okay, you can go back and check again. Our output of coming from some layer and the identity function. We are basically combine the summation. Okay, that may create impede information flow in the network in some cases. And that in that case, what we are doing, we are to further improve the information flow. We are changing the connectivity pattern a bit. We are incorporating direct connections from any layer to all the subsequent layers in a particular DenseNet block. So it is not that we are considering the DenseNet through the whole network, because that will be too huge. When you are passing this information to all the networks like this, and so on, it will be too huge to pass. And there again, there are some problems associated with that. Hence, within the DenseNet, we are considering smaller blocks. And within the smaller blocks, here in ResNet, the main difference is that here this identity shortcut, we are passing to some blocks, not all blocks. In DenseNet, the main difference in that, to improve the information flow, we are passing the information from a particular block to all the subsequent layers. From one layer inside one block to all the subsequent layers. So these are block is the whole thing, mind it, this are the layers. So we are passing the information from one layer to all the subsequent layers. That is the only change. There are some few little, not so significant changes, but this is the main change in DenseNet concept. Okay, so whatever we have discussed so far, this is basically that how we are handling the depth. That's why we are terming them as, from the first we have talked about, this is multipath also, because multipath based CNN. Now I think no need to explain why we are terming this multipath CNN. You have one highway path and one normal path. And also we are terming them as, if you go back, depth-based CNN. Okay, we have some strategy to handle large depth, because you can see here, if we go to this DenseNet, so it can actually multiple paths or shortcut connections, and it can support actually huge number of layers. DenseNet can support ResNet also. You can see here in ResNet it is so many times deeper than AlexNet or VGG. Okay, and it can go up to this type of 152 layers, even higher. Okay, less error on image classification than 34 layers. That means the significant thing is that it can handle up to this much of layer, whereas in GoogleNet we started in LeanNet with 5 layers, then we came to AlexNet with 8 layers. From there we came to this GoogleNet, we came to around 22 layers. From there, with this highway network, with this handling this gradient problem properly, in ResNet, we are talking about 162 layers. So this much huge number of layers we can handle, and the more we increase the layer, of course, we can handle complex scenarios, complex images, and more complex features we can actually classify with high accuracy. So that is the importance why we are interested so much to increase the number of layers. So then instead, of course, the number of layers are almost similar, but we are actually improving in terms of information flow. Okay. Then comes one last one we will discuss today, that is the depth with depth. Okay, it is also called depth-wise separable. So as the name suggests, from this diagram you can see you have multiple channels. You can term them as depths, and you are separating them in terms of initially whatever we have discussed from our basic understanding. We have separated them in a depth-wise fashion. We have taken separate channels, and there we have applied n cross n convolution. That we have discussed, right? In our special context also, we have done the same. We have taken separately the channels, and on top of that, we have applied this type of convolution. And we have extracted multiple features, etc. And then finally, it is possible that we have added point-wise convolution, where we have fused the effect of multiple channels, and then finally we have focused on the features that we are taking into account while doing the final classification. Now, exception, maybe that is extreme inception. Now, inception block, you have seen today that it is considering smaller blocks, and they are having in layers. We have the concept of split and then merge, split, transform, merge. The same thing you are applying, but it is in modified depth-wise separable convolution. What we are doing here, a big change is that here all these channels, on top of all these channels, you are first applying this 1 cross 1 convolution. That means you are fusing the effects of all these channels. Okay, and then you are getting some output. On that output, then you are basically applying, according to the depth of that output, you are applying this depth-wise convolution. Okay. And then that is quite similar, that you are applying this n cross n convolution based on features. You are separating the features. Maybe after that you can again apply this type of 1 cross 1 convolution, or you can keep it separate. That is based on your application, based on type of the features you are actually choosing. So this is the basic concept of exception, that is called extreme inception. Because in case of exception, what we are doing, we are taking the concept of inception itself, where we have initially applied this 1 cross 1 convolution, and then we separately done this n cross n convolution. Okay, but this is that time we have, if you go back on to this inception part, what we have discussed, you can see we have splitted, and then we have partly applied this type of convolution, 1 cross 1 convolution. But here this exception, that's why it is telling that extreme inception, where you are making it in one shot. You are applying this 1 cross this point-wise convolution, or 1 cross 1 convolution at one shot. Then you are going for this n cross n convolution. Okay, this is one modification that proved to be effective in some scenarios, like detecting phase swaps in videos, and some other related video processing related CNNs. In this case also, it is not shown here, but in exception also, the usage of ResNet concept, that means this usage of this residual network, that also added incorporate converted, and it has shown some significant amount of efficiency to achieve some usable accuracy in this type of application, these webs. Okay. So with this, just we have discussed about one thing. This example for applications, you can go through some links in that will appear in Google. But if you are interested for any of this, CNN concepts, always read from the actual papers. The mother paper that is actually, telling you the literature and actually proposing the new concept. Whenever it's an easy way to search. If you are not finding everything in the book, when you search in Wikipedia, don't read in the Wikipedia. There is a go to the reference and check for the first or second reference. That is the main mother paper. So make a habit whenever, if you are interested at particular portion, because this is, see, we are in this course, we are not discussing about this all the details of these blocks, right? Maybe I have given a very short overview that what type of layers are there, what type of requirements of here, how many huge number of layers we are going to handle. And in the next discussion, basically we will start about the embedded scenario. We will revisit this architecture and we will see that this architecture is so much huge. So we cannot take everything for our embedded scenario, but we will optimize some part. We will take a reduced version of it maybe, and we will see whether that is working fine in embedded scenario or not, and whether that is giving you manageable accuracy, usable accuracy or not. That we will discuss. So we will come back maybe some of this the structures again and again then that time. But if you are interested to know what is the more modifications in these blocks, in these modules, always go through these mother papers that you will find in Wikipedia. Just give the name, but go to the reference or first one or two. Those are the actually written by the authors, when actually proposed by the authors. Read that one. That will clear most of your doubts. Okay, so that's all for today. So there are again more variations. I'm not going to discuss all of them. There are some attention-based CNN, some feature map exploitation, and many more. So, but so far, whatever we have discussed, I think you have some idea that how many layers we can actually use. What may be the requirement based on applications? What may be the requirement? How many these layers may vary? Maybe when we are thinking of designing one application for handwriting detection or digit detection, that time we may not use one huge dense net. That time LeNet is sufficient. But when we are thinking about some this video related issues, face swapping detection, etc., that time we need to think about some advanced this type of model. So based on our requirement, we will see more that in our embedded discussion. That based on our requirement, we will choose, we will optimize, and we will select this type of layers. We will select this type of architectures, and then we'll see what type of modifications we have to do. For to realize them in our embedded platform. Okay. Any question? If you have, I'm sure you will have multiple questions because what? Okay. So do you want? You can ask me now, or maybe next day we can take up the questions. Do you have anything to ask, or any part you want that one thing that that Google Net structure that we will maybe take up next day with a more detail with the proper architecture, so how that concatenation is working. Anything else?
Ma'am, when will the embedded part start?
Yeah, from tomorrow onwards.
Okay.
Tomorrow I will give some introduction to embedded with that part, and then from tomorrow onwards we will discuss about the embedded. Okay. 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 If there is nothing much, then we can wrap up today. Okay. Tomorrow we'll start discussing about the embedded challenges. Okay. Thank you. If you want to ask any question, I can answer. Okay. Yep. Okay.
Thank you.
Thank you, ma'am.
Right.